Welcome back to a lecture series on molecular simulations and statistical mechanics. In the first 10 lectures, what we've seen is classical mechanics and how particles move and interact with each other. We've seen thermodynamics, in which we lost that information and we started to study systems from a more macroscopic perspective. But naturally, we would wonder if we could connect the two. We wonder if, for instance, the motions of a lot of atoms and particles actually give rise to those thermodynamic properties that we discussed in the last few lectures. And the answer is contained within the field of statistical mechanics. So statistical mechanics is going to be a way for us to bridge these sort of microscopic pictures, this atomic scale picture of matter, with our intuition and our thermodynamic picture of matter that's more at the macroscopic scale. So to think about this, the first thing I want to talk about is measurements. When you go into a lab and you take a measurement, right? You go in and you stick a thermometer in a cup, or you measure something, right? Like you put a ruler up to something to measure its length. What do you actually observe? So what we're going to say is, suppose we want to measure a dynamical variable. Suppose we want to measure some dynamical variable. And a dynamical variable, remember, is just a variable that depends on the relative positions of the particles, the momenta of the particles, and time. We want to measure this, right? Well, when we make the measurement at some time. So we can call that the A experiment of t. And the question is this equal to the value of A at t, right? Is this equal to A of when all the QFs are at their specific positions at time t, all the PFs are at their specific momenta at t, and t? So what this line amounts to saying is, when we measure something in the lab, are we just measuring this dynamical variable at a fixed time? Let's explore this more deeply with an example. So in this example, we're going to be measuring the length of a rod. Seems pretty easy, right? You just hold up a ruler to it and you say, oh, okay, it's this length, right? But at the atomic scale, there's a bunch of atoms in the rod bouncing around. And there's atoms on the end of the rod that are vibrating, right? So defining the length of the rod is not actually so simple as just holding up a ruler to it, right? These atoms are bouncing around, moving, changing the length of the rod. So what we'll do is we'll define the length of the rod at any time to be the largest distance between atoms in the rod. So the furthest atoms apart, we'll call that L. Now L is a dynamical variable, right? Because it depends on the relative positions of the atoms, their momenta, and time. And what we're going to say, more formally than what we intuitively said, is that this L is equal to the maximum distance in the x direction between particles in the system at time t. So basically all this notation says is that if we looked at every single pair of particles in the system, which one has the maximum difference in the x direction compared, and that would be equal to the L. So we could say this is the y direction, this is the x direction. Now what's interesting, right, is this L is changing at the time scale that these atoms are moving, right? So at what time scale do atoms vibrate around? Well, that happens at about the order of 10 to the minus 12 seconds. So this length is changing at approximate amounts of time of 10 to the minus 12 seconds. Well, when you measure something, right, even if you held up a ruler, let's say you came over here and you held up a ruler and you went to measure the length of this thing. And instead of using your eyes, you wanted to be more precise, so you took a picture to then compare later, right? The amount of time that a picture can resolve, even an advanced picture, is around 10 to the minus 4 seconds. So this is for atomic motion, is 10 to the minus 12. And this is for let's say a photo measurement. Looking at the difference in these scales reveals that over the time that this measurement is taken, that the atoms will go through approximately 10 to the 8 vibrations. 10 to the 8 vibrations over the amount of time that we measured it. That's an extremely large number of changes in this system, right? So the idea is that even when we go and observe something like this at a macroscopic scale, the atoms have gone through a ton of different configurations that we can't resolve. So what we really observe when we look at a measurement is the average of that measurement over all of these possible states that are in between. If we could keep track of all the atomic motions, we could always know what L actually is. But in reality, that's not the case. And especially at our scale, at the macroscopic scale, we are not able to see these atoms anymore. So the idea and sort of the driving force behind statistical mechanics is to write out ways to understand these dynamical variable properties in the context of averages and how we measure things as averages. So how do we express an average mathematically in this sense? Well, I'm going to propose, let me switch marker colors here so it's easier to see. I'm going to propose the following definition, and then let's break it apart a little bit. So if L at a specific time t is the maximum, then what we'll say is that the measurement, or Lx of t, is equal to the limit as tau goes to infinity. Tau is going to be how long you take the measurement, of 1 over tau times the integral of L QF PF t dt, so that it's a time integral, and the time integral will go between some time t over the duration of time tau that you measure it, starting from t. So what does this look like? Well, all we're saying is that if we could sit here and measure something for an infinitely long amount of time, tau going to infinity, and we could add up the contributions, or add up L over all of that time, and divide by that time, that we would get our expected value. So what does that sound like? Well, let's think about another example here. Suppose you went to the lab and you took 10 measurements, right? So let's say you took x1 through x10, and you're measuring some property. Well, when we did some statistical analysis on these measurements, what would you do? Well, maybe the first thing you do is look for the average. The average is just equal to, so the average is just equal to the sum of all of the measurements you made, right, divided by the number of measurements. This gave you your average x. Well, in this case, we're actually doing the same thing. It's just that now we have a continuous variable in time. Whenever we have a continuous variable, we switch our discrete summation to an integral, right? So what we're saying is let's add up all of these measurements over the time that we measure it and divide by the total time that we measure it. It's the same as adding up all the measurements we made divided by the amount of measurements, right? So this is just an average. And of course, we include this limit to say that we need to technically measure this for a long enough time that we actually can resolve what the average is. For instance, if we didn't measure long enough and there were fluctuations in the system that were happening over a longer time scale, we wouldn't actually get to know what Lx was because we only are capturing a tiny fraction of its motion. So in general, the measurement or the expectation of some dynamical variable we can write as this average, the limit as tau goes to infinity, as our measurement time goes to infinity, of 1 over tau of the time integral of A over the measurement time. So to summarize, we are just looking at A for a long time, right? Adding up all of the values of it and dividing by the total time we measure. This is an average. So now that we understand how to take measurements, let's start to get into the notation of statistical mechanics and sort of the language of it. So the first concept to introduce is something known as a phase space. Phase space is defined in the following way. Recall that the mechanical state of a system was specified by 2f coordinates. The mechanical state of a system is specified by 2f coordinates. And these coordinates were the velocities, or the positions, Q1 through QF, and the momenta, P1 through PF. So depending on how many particles you have, we call that F, you have different numbers of possible variables that describe the mechanical state. Now what we'll say is that the space spanned by these variables is called a phase space. Now what do I mean by spanned by these variables? Well, for instance, if you are in three-dimensional space, like an XYZ plane, or an XYZ space here, to make this space, you have three vectors, right? You have a unit vector in the X direction, in the Y direction, and in the Z direction. These vectors, whenever you can create out of them, so if you can take a vector like the unit vector in X and multiply it by a number and add it to the unit vector in Y and multiply it by another number, and Z, multiply it by another number, any vector you can create using this method is spanned by this space. So really it is just creating this entire three-dimensional space. In this case, we have a 2f dimensional space. This 2f dimensional space we can't visualize like we just drew on the board here, but this is called a phase space. So this 2f dimensional space is a phase space. So we're moving away from your normal three-dimensional case, and we're starting to get into some very, very high-dimensional systems here. Some other notation, a point in the phase space, so a particular state, we could say, a particular Q1, we'll say Q1 prime, QF prime, P1 prime, PF prime. A particular state in the system, in the phase space, is called a phase point. And finally, the time evolution of a phase point, is called a phase trajectory. Is a phase trajectory. So let's quickly think about what a phase trajectory is. If I'm in my phase space, let's say, we'll do example 1 here. If I'm in a phase space, a phase trajectory is I start at a point, and that point starts moving around in this 2F dimensional space. Okay, makes sense. But let's think about what other types of trajectories you could have. You may have trajectories that are periodic. For instance, you start somewhere, the system starts evolving, and then it just goes in a cycle and goes back to its original point. And it just keeps looping around. One system that's like this is something like the harmonic oscillator. The system keeps returning to the same positions and momenta over and over and over again, assuming there's no friction or something like that. Now, are there any phase trajectories that are not possible? Well, one, and I'll draw it up here, one that is impossible is if you have a phase point that starts going, and then it starts to make a loop, it comes back and hits where it originally has been before, and then goes in a separate direction. The reason that this cannot happen is because the Hamiltonian of the system should fully specify the time evolution of the particle in the system, or of the phase point in the system. So what happens is if you were traveling along this path and you hit this point, and at one point you went in this direction, well, the Hamiltonian should fully specify that. When it flips back around and you hit the point again, if you go in a different direction, you're violating the fact that the Hamiltonian is fully specifying the next step, the time evolution, right? Because you've just gone a completely different way. So this type of phase trajectory is not possible. Now, if you missed the line, let's say maybe you went underneath it or something, you would be okay. So these are just some definitions. So the important ones are this average that we've defined here, the statistical average, or we'll say this is a time average. This phase space, a point in the phase space called a phase point, and then trajectories of points in phase space. And we've seen ones that are realistic and ones that are not. So we've introduced some notation and definitions to understand the space that these statistical mechanical particles behave in and live in, right? But now let's sort of think about how can we describe probabilities in this space, or the likelihood of points existing in certain regions of the space, right? So how would we even start to do that? Well, suppose within our phase space, we drew some volume element, and I'm just going to represent that like this, dqf dpf. Of course, this is a 2f dimensional hypercube, but for our purposes, I'm going to draw it in 2 dimensions, right? Well, the phase trajectory, right, your system, might pass through this guy, right? You know, it may not stay there forever. It might go and, you know, do its own thing later on, right? But you'll end up with something like this, right? What is the probability, if I just stepped away from the system and I had you walk up to it and tell me, what is the probability of finding this system inside of this hypercube? Well, you might say, okay, well, one thing that makes sense is if I sat here and looked at the system for an extremely long amount of time, how much time is it in the cube versus not in the cube, right? So that's a pretty intuitive way to think about it. And we're actually going to define a function called rho, and this is going to be a function of the QF, PF, and T's. Rho times the volume of this cube is going to be defined as how much time the system spends in the hypercube, which we're going to say is delta T, which depends on the QF, PF, and T, divided by the amount of time we observed the system. Now, in order for this to be an accurate probability, we need to observe the system for a long time. So we include the fact that we need to take the limit as tau goes to infinity here. So this is kind of an intuitive definition, but what is rho, right? So what we've said is, okay, the probability of finding the phase space, or finding the point in this region of phase space, is given by some expression that looks like this, right? So that means this represents a probability, right? So we have a probability times a volume, right? So this is a probability per volume, right? In other words, rho is a probability density. This is a probability density function. It's actually quite similar if you think of from your maybe multivariable calculus days when you had a problem that gave you some weird volume to deal with in 3 dimensions and then assigned a mass probability, something that was rho was in units of mass per volume, right? And to find the total mass of the system, you had to do a triple integral over every direction of rho, right? dx, dy, dz, and that would give you the total mass, right? Well, this is the exact same thing, right? If we have rho here, this is like a probability density function. We integrate over the volume, and that gives us the probability of observing the particle within that specific region of the space. Now, let's think about what a probability density function is. Well, first of all, in order for a function to be a probability, it must normalize to 1. Why is that? Well, we can write that condition first. Let's write it down. That if you integrate it over the entire space, over rho, over the entire space dqf dpf, that it must equal 1. This is called a normalization condition. Why does this make sense? Well, intuitively, if the particle could be anywhere in the space, right? So the system could be anywhere, and since we're integrating over the entire space, we are essentially saying that the probability the particle is at least somewhere is 1 or 100%. It's definitely in the space, right? A way to think about that with an example is imagine you have a 6-sided die, right? When you roll a 6-sided die, that's fair. There's a 1/6 probability of rolling each side, right? You could roll side 1, would be 1/6, side 2 would be 1/6. We'd add those up over 6 sides. You'd end up with just 1, right? So this is the idea. You flip a coin, a fair coin has a 50-50 chance of flipping heads or tails. probability of one side is 0.5, probability of the other side is 0.5. They always add up to 1. This is just a slightly, it's not a more complicated concept, but we're in a much higher dimensional space with many, many more elements in the problem, because now rather than have discrete events that can happen that add up to 1, we now have a continuum of possible events that can happen that must add up to 1. So this function has to be normalizable over this entire space, right? So there are many functions that do that, but we're going to have to look for specific ones that also satisfy other properties. But it's really important to understand this normalization condition. Very important. Intuitively, because this is an integral, you can think of, if I'm looking at a simple one-dimensional case here, a probability distribution like a Gaussian will have a shape like this. If I integrate it over the entire x direction, in order for it to equal 1 or be finite at all, it must start infinitely closely approaching 0 way out in x, right? So this must behave in the same intuitive way as this, right? So this is condition 1. The second condition that's important is that rho cannot be negative. It's a non-negative quantity. That's because probabilities don't make sense if they're negative. You can only have the probability of 0, in which there is no chance an event will happen, or a non-zero probability that's positive and less than 1. So we have this definition for rho, describing the probability of observing a point in the phase space, but have we really done anything, right? All we've done is we've kicked this problem of understanding the system to a completely different problem, right? We've just introduced a new function. But let's think about what this function means with respect to our averages. So what we can do is we can actually write, using this rho, right? Recall that when we were measuring a dynamical variable, we said that the expected value, or the measured value, was the limit as our measurement time got really long of 1 over our measurement time integrated over the course of the measurement, pf t dt. Now notice, we have this lim of tau to infinity, as tau goes to infinity of 1 over tau. Here we have a lim as tau goes to infinity of 1 over tau, right? And we have this dt, right? So in the infinitesimal limit, this would be a dt, not necessarily a delta t, right? Well, that's all just contained here. So naturally, we could do a change of variables on this integral and rewrite this expected value in terms of this probability density function. And we can do that in the following way. We can say that the integral now goes over the volume of phase space of this is just equal to rho, right? Rho times A, and I'll leave off all of these dependencies, but these are here just for board space. And now instead of dt, we have dqf, dpf. So we've changed the problem. We've changed the nature of the problem. In this case, we would need to observe A over a long amount of time. So solve equations of motion, something like this, which would be completely infeasible for a giant system like a cup of coffee, right? But now we've kicked it to a new problem where we have this integral of some function rho times that variable integrated over the entire volume of the phase space. So we've changed the nature of the problem. The question is, why did we do this? Why introduce rho? the hope and really what we're driving at is that by introducing rho, if we can find a rho, if we find a rho that works, in principle, we can actually solve this integral without ever solving the equations of motion. If we find a rho, so not necessarily calculate a rho like this, but if we can find a functional form for it, we can solve for our observables, for our dynamical variables, for A's, without solving the equations of motion. Without solving the EOMs, the equations of motion. So the reason we're doing this is to hopefully simplify this problem in a way that allows us to then do deeper physics without having to do Hamilton's equation of motion on 10 to the 24 particles in order to understand what's going on. Another reason that we introduce rho is that it gives us a different way of thinking about the problem, right? So before we were like very intuitively saying, oh, we'll just take the average of all of our measurements and that will give us our expectation. Well, we're saying the same thing, but now we have an object that's a probability density function, and it gives us unique ways of thinking about the problem that are going to actually lead us to intuitive and very straightforward definitions of things like entropy and free energy, which we'll see in the next lecture. Now let's talk about the case of statistical equilibrium. So what happens at equilibrium? Well, recall that that at equilibrium, the time derivative of our dynamical variables is 0. And we also have that this guy does not depend explicitly on time, right? So we're sort of in this steady situation in which there are no changes in time with respect to our observations, right? Okay, well, let's write this out in terms of the definition of the derivative. This derivative is the same as saying the limit as delta t goes to 0 of 1 over delta t times ax at t plus delta t minus ax at t. Now we have definitions for these based on our probability density function, right? So let's just write those in. This is equal to the lim as delta t goes to 0 of 1 over delta t times, we now have this guy is equal to the integral over the phase space, right, which I'm denoting as v, of a qf pf. Now we don't have explicit time dependence because we're at equilibrium, right? So a qf pf, rho qf pf, and t, rho could change in time, right? We've made no restrictions on rho. And of course, this is at t plus delta t. And then we have minus, I'm just going to move them all under one integral sign, minus a qf pf times rho of qf pf t. And this is at integrated over the volume dqf dpf. Maybe give some brackets here to specify what the integral is taken over. So what do we have? Well, we have the same value, a and a, so we can pull them out. And then we have a difference in rho at t plus delta t and rho at t. We've done this many times in the class. We're going to invoke a first order Taylor expansion on these terms so that we can write rho, this difference, qf pf at t plus delta t minus rho of qf pf at t. We're going to write this with a first order Taylor expansion as partial rho partial t dt, right? This is a first order Taylor expansion. Well, that means our equation now becomes the lim as delta t goes to 0 of 1 over delta t times, we have the integral of a times this derivative integrated over the entire space. Delta t is not affected by this integral, it's a constant, so we can pull it out and it's going to cancel with this delta t. We now have no delta t dependence in the equation, so this limit doesn't matter, we can ignore it. And what we're left with at the end of it all is that 0, remember because we have 0, is equal to this integral over the phase space of a qf pf partial rho partial t dqf dpf. Now this must hold for any choice of a. Regardless of whatever a I choose, this must equal 0. The only way for that to hold is if partial rho partial t is equal to 0 everywhere and at all time. And at all times, it must always equal 0. So we've just found that rho, or partial t, is 0 everywhere and at all time, meaning that rho does not depend explicitly on time. Rho doesn't depend explicitly on time. This is an important result, and of course this is at equilibrium. At equilibrium. Now let's talk about the concept of a statistical ensemble. What do we mean by a statistical ensemble? So recall that rho was constructed by looking at a single system evolving along some phase trajectory. We said, how much time does the system spend in here? Delta t over how much time do we measure it, and let's measure that for a long time. And this was defined as the probability of observing the system in this volume element, right? But that's only a single system. A statistical ensemble is essentially just if we imagine that our system had multiple copies or a large number of equivalent copies. And when I say equivalence, I mean equivalence in a very specific way. So let's think about what that means. So let's suppose I have some phase space here, and I've got a phase trajectory, right? And then I made an identical copy, and I started the system at a different point. It would have a different evolution, right? So maybe something else would happen. And I made another copy. And I put this here. And it started to go that way. And I did that for a very large amount of time, or a large number of copies. This is an ensemble. So this collection of copies is an ensemble. collection of system copies. This is an ensemble. So what are some requirements for the copies? Notice, even in the way I drew this, the state of the system, the trajectory of the system does not have to be the same. It does not have to be identical. So the mechanical state can be different. What can't be different is the specific form of the Hamiltonian that these phase trajectories evolve by. So the Hamiltonian must be the same. Hamiltonian must be the same. So our ensemble is a collection of, and we'll say the number of copies is given by this variable, this curly n. So the ensemble is a collection of n copies of a system with the same Hamiltonian. The same Hamiltonian. So the only sense that these guys are identical is the fact that their Hamiltonian is the same. They obey the exact same time evolution, but they may be in completely different states, right? So now you could ask, right? So this was sort of our single system case for the probability, right? But what about in the ensemble case now? Let's look at the ensemble case. In the ensemble, you could ask not just what's the probability of observing one system in the volume element, but how many systems are in the volume element? What is the what is the number of systems that are in the volume element, right? How do we predict that on average? Well, because we have this row, we know the probability that a single system is in there. So to get the number of copies, we just have to multiply by however many copies are in the ensemble. So we can actually calculate the expected number of copies, in a volume element dQf dPf by evaluating n, the number of copies, times rho dQf dPf. So this will tell us the expected number of copies of the system that are at a specific region or volume in the phase space. So I've drawn, maybe 3 of the copies are in the phase space and the rest are not, right? Well, that is reflected in this function, right? And what we're going to show next time is that the number of copies in the phase space, or the number of copies that are in certain elements of the phase space, is actually conserved. This will be the Liouville theorem that we'll do at the start of next lecture. But really the whole point of this lecture is just to introduce you to some notation, some concepts in statistical mechanics, and the notion specifically of these ensembles. So imagine these vast collections of systems. If you could have a really large number of them, that's ideal. And with ensembles, we're looking at, okay, what are the averages of the behavior in these ensembles, which we can look at through something like this expected number of copies in a specific region. So thank you guys very much for listening. Next time we're going to be doing Liouville's theorem and introducing a functional form for rho and seeing what the consequences are, including deriving some microscopic definitions for entropy and the Helmholtz free energy. So thank you very much, and hope to see you next time.